Three, everybody knows my rule. I start at 3 minutes after. So I'm really happy today to introduce our first AI forum speaker for this semester, Jesse Thomason. So a lot of you know Jesse because he used to be here. So I have to give the basic background. He grew up in Arkansas. Then he did his undergraduate at Pitt, where he started working in language with Diane Littman. Is she retired yet, actually?
I just started.
And then Jesse did his PhD here with me. Peter was on his committee. Who else was on your committee?
Scott and Stephanie.
And we were talking. It's actually shocking to me. He left 7 years ago now with his PhD. He did a postdoc at UW with Luke Settlemeyer and Dieter Fox. Did a short postdoc at Amazon, right? And then he's been for the last several years at USC in Los Angeles. Of course, I'm the one that contaminated him with the importance of language grounding, and he's continued to work in the area of language for robotics, and he'll tell us about a lot of that today. One interesting thing that I talked to one of his students at NACL, we were both at NACL in Albuquerque back in late May, is working on another interesting topic. I don't know if you're going to talk about this, which is sign language interpretation. There's another new topic he's gotten into recently. But I look forward to hearing about what he's been up to lately. Everyone knows I have to have an anecdote when I introduce a speaker. I was trying to think about this. Maybe my best one is apparently Jesse does a really great impression of me. I've never actually asked him offline to do his impression of me and see how good it is. Apparently, it's pretty good. Okay.
Maybe you're not going to tell us if he's giving you any academic grandchildren?
Oh, yes, 2 already, and more on the way.
All right.
Yeah, thanks, Ray, for that detailed intro. So I do still work on language and robots. When did GPT-4 come out? Like 2 years ago? 2 years ago-ish, I was at NACL or one of the Star CL conferences, and another of my NLP colleagues came up to me and was like, "You still doing language and robots?" I said, "Yes." He said, "Didn't GPT solve that?" That upset me, but they're not totally wrong. So this is a paper from 2020. I've got a handful here from the last 5 years. This paper is one of the first things to do language and robots with deep learning in a way that worked. This is a small paper from Google called Language Conditioned Imitation Learning over unstructured data. They later followed up with one called Learning Language from Play. Basically, they jointly embedded state action goal images and state action language into a central embedding space. And then that means at inference time, they can just look up the nearest embedding and do basically nearest neighbor search to retrieve the trajectory. But the language is really boring, right? Open the door, pick up, push red button. 2023, we get the RT2, the first transformer directly predicting low-level actions for closed loop control. But it's still put the X in the Y, pick up the X, pick up the X. I don't know, pick up the X and put it on the Y as Sherdlu, right? We've been doing this for decades and decades in blocks worlds. There's a little bit of interesting work in language and robots. Some of it's from my lab, obviously I think so. And then work on how to do things or what constraints to follow, I think is genuinely pretty interesting. But there's not a ton of this, right, in the shared autonomy space. So the research question I've been trying to ask through my lab in the last couple of years is how can we better enable human AI communication by thinking about where language actually comes from, thinking about assumed mutual understanding between our interlocutors. So when I am talking to a person, I know they have a world model. I know they have thoughts about me. I can give them much shorter commands. I don't know. I'm not limited to pick and place when I talk to a person. And so I've been tackling this from a couple different angles. We've got language and logic, which is where I'll spend the majority of the time today talking about trying to fuse powerful neural models with more traditional symbolic planning. Introspection and interaction, where we're getting into things like VLAs, LLMs, et cetera. These are just forward inference machines, which means if I put something into it, it will produce output, and it might produce output when it ought not to, especially with robot control. And I'm going to talk a little bit about processing beyond text, which is our work in sign language and speech, which I think, in general, this is a thing that's very interesting and should be a thing NLP cares about. But there's a running joke in the NLP community for the last couple of years that it's become in a transformer engineering field, not a language field. And so looking back at, communication outside of pure text, I think is interesting. And there's fun stuff to do with robots there. So I'll start with language and logic. So a few years ago, we released this paper, Prog Prompt. This is using a language model as an open loop world agnostic planner. This is it has become a common thing to do. Even just now, one of Justin's undergrad showed me a demo where they're calling GPT to write little snippets of code that call high level APIs. This is like part of the stack now, but we did it first. Coders policies came out at the same time, same conference, both did it correct. And so the idea here is if I have an intent, like I want a meal, I could tell a robot, reheat dinner. If I tell a person that, they'll be able to do it, obviously. If I tell a home robot, you might be able to get a language model to just dump out like a reasonable set of API steps to do this. Grab some chicken from the fridge, turn on the stove. But unless we ground this in the world and ground it to the robot's capabilities, we get issues. Like maybe there's no chicken in the fridge. That's easy to fix. Just tell us what's there. But it gets trickier. Like we do use turning on stove, even in like RL bench. This is one of the tasks. I don't want my robot to ever turn on the stove, especially a gas stove. But in general, like I don't actually want the robot near fire. And also, most robots are one-handed. Like unless we're using a bimanual manipulator, I actually can't grab the pan because I've already grabbed the chicken. My hands are full. And so making these language models world aware basically solves this problem. All I need to do is include the shared world I have with the agent. So include the fact that we are in fact like in the same room, speaking the same language, we have the same world model. And if I dump that world info in here, the inside is just knowing what objects are in the world and what actions I'm capable of doing can discourage this kind of planning hallucination for these open loop planners. And so I get a plan that maybe is reasonable now using the microwave and something that's actually in my fridge. And the fun part here is the code generation. So we basically made it look like Python. So we say we've got an actions library that tells us what we can do. We dump the objects in as just strings that are available, give some in-context learning of some example like functions we could do, like throwing away a line. And then our prompt is just to say, here's the next thing you should do, microwave salmon. And we generate this plan. It's largely open loop. We've got a few like failure conditions in here. Like if the microwave is closed, I now need to open it first. So it's got little like single step recovery, but it is open loop. Like once we start executing, we don't revisit the code generation in this paper. And in the end, we get our little avatar in the simulator, goes, grabs some salmon, puts it in the microwave and heats it up. You can tell that a graduate student put this together because they think it's acceptable to microwave salmon. Don't microwave salmon, guys. Especially not in a public place, but even in your house. Don't.
But when you say it's open loop, it's not, because if it's got recovery, then it's not actually open loop. Not that it's not mixing planning and execution.
What I mean to say is that the plan generation is open loop. The plan itself has little single step recovery in it. We don't have a bit to identify that like my preconditions have failed. I need to replan. That doesn't happen. If I do an action and it fails, I just stop executing. I draw this distinction only because I'm going to do closed loop more properly in a minute. Does that make sense?
Yeah, I would just say it's not replanning or it's not mixing planning and execution, but it's still closed loop if there's any kind of sensing in it.
I appreciate that. Okay. It's not replanning. Okay, so the fun bit here for me as a person who spent their whole PhD doing pick and place of objects from one place to another, is I can give a task like sort the fruits in the plate and the bottle in the box, and the robot will do it. It will do it despite the fact that I didn't tell it what fruit is. I know this is not impressive to people who've been using language models for a long time, but when this happened, it blew my mind because I spent grad school making word lists of things the robot could understand, and then transferring the word list into things in the real world that correspond to objects and doing some kind of like grounding on colors and shapes. And now a language model can just do this, right? We get a visual observation, we run segment anything or so on it. We say, here's some bananas and strawberries and plates, and the language model can work with that. The deal is, we already know how to do symbolic planning. Like if I did know where the strawberry and the banana were, I should be able to just make a plan to put them down without invoking ChatGPT. So what large language models are giving us is cheaply defined domains in my head. Like I can give you like, here's your actions, here's objects in the world, and it will kind of do common sense planning. But the plans are noisy, they're imperfect, often they're actual garbage. If you've been using them every now and then, they will just catastrophically fail.
Yeah, Carson has shown a version of the demo you saw where he basically verbally programs it. I think Peter's, yeah.
even with an interpreter, which we're using here to like take the code and try to translate it into what the robot API can actually do, we can fail to meet action preconditions. Like say I try to open the microwave, but it's actually not like a push button. It needs me to like pull the handle, and I've already got something in my hand. Then I've like suddenly failed because the microwave doesn't look the way I thought it did. And I can attempt actions on incompatible objects. But I guess we're probably still working on calling the elevator, right? Or like opening a very heavy door. Like open door should be reasonable, but there are some doors you can't open with a mobile manipulator. They're too heavy. With symbolic reasoning, by contrast, we have very expensive domain knowledge. We're talking like traditional things like PDDL or integer linear programming style solving. So we have very expensive domain knowledge to write out how the world works. Once I've got it, I get perfect plans. Perfect to the degree that my domain knowledge is perfect. So just as a quick recap on what symbolic planning can look like, this is a domain file. This is PDDL. So we've got a blocks world domain. I'm going to say some predicates. This is things that can be true or false. So something can be clear. It can be on the table. My arm can be empty. I can be holding something, and something can be on something else. With this is sufficient for me to define like stacks of blocks in the world. And then I define my actions. Like I have an action that says put something down. To put something down, I have preconditions that'll be like I have something in my hand and the thing I'm trying to put down on is clear on the top. And my post conditions are things like my arm is now empty and the thing is on top of the thing. Now I've got a problem file that defines the world. So this is a really small world we've got here, but we've got perfect domain knowledge that tells us like, here's the current version of the world, this initial state. And my goal is to redo the stack so that it looks like this. So we've got our domain file, our little problem file. There are many little symbolic solver libraries we can then invoke that basically do something smarter than the breadth first search I'll show here, where we explore possible actions and their outcomes until we find a path from the start to the goal. Make sense? And then our path is our plan. These are the actions I should take in this order to get to the end goal as quickly as possible. So, annotating this domain, an expert needs to write down all the action pre and post conditions and this big object type taxonomy. Like in this example with fruits, I would need to explicitly say banana and strawberry exist, and they are both of the category fruit. Like that would have to be a predicate that I've got that defines this thing. It's been a long time since we needed to use WordNet, but that would have been the way to do this back in my day. Do we have to choose? My research says no. So this first bit that we presented at NACL last year is what if we could take away just a little bit of the expert annotator's work? And the bit that we take away is action pre and post conditions. What if I look at this like prog prompt code as policy style work where we're predicting a high level API action like pick, place, go to, and I say, okay, you can put things down, you can unstack them. I give you the name of the action you can take. Can I learn when I can and can't do these things? If I can, then I'll get perfect plans and I'll get a cheaply defined domain. So our insight is going to be to use large pre-trained models to iteratively guess pre and post conditions and then try them out, our little robot scientist. So this is going to be our basic learning loop. We'll have some memory that we're maintaining. This is our hypothesis space of possible pre and post conditions for each of our actions. We'll sample a concrete domain file where we say, like, I think this is how the world works. I'm going to give it a go. Make a plan, try to execute the plan in the environment, find out what fails, and then invoke a language model on failure to look at the error messages, look at what I was doing at the time, how the world state has been changing, and make guesses about what the pre and post conditions ought to have been, update our memory, and go again. So this memory is going to look like a list for every pre and post condition for every action. It's a very simple memory structure. Each memory is going to be associated with a weight, and then we just do simple Bayesian updates to these weights. If we keep believing in a particular precondition, we'll update its weight, and if we didn't use it or we actively found that it's not true, we'll downgrade its weight. And then we sample from this from a binary distribution for each of these every time we sample a concrete file.
So purely correlations, no causal model? Or are you going to do probing for causality?
There's no causal model in this one, but there will be.
I've got a question.
Yeah.
How are you grounding those semantics? Like, do you have something that's the extractors, are you on table or clear in your, like, is there a vision model or something that's providing? That
This one will be only symbolic domains. So we're going to look at the traditional domains used for people who run like planning competitions to write faster solvers. So they're simple domains for the most part. And once we learn those, we'll move on to real world, and then we'll use VLMs to do this part. Yeah, that's true.
So.
Yep.
To get kind of into the details of the PDDL here,
Mhm.
you've got unstack object one, object two. Right?
Yeah.
Now, that means picking up object one from being on top of object two, right? For the actual robot action, you don't care about object two, right? The reason you have object two as an action parameter is for the symbolic planning
Exactly.
to update the status of object two to be clear, right?
Yes.
And so if I was starting from scratch, right, without knowing anything about symbolic planning, you wouldn't even know that unstack needs two parameters and not just one.
That's correct. And a big weakness of this approach, both this and when I move to like real robot stuff, is that I do still have to say the names of the actions, and I have to say how many parameters they take, what the types of parameters are. I'm allowing this because of this analogy to this like open loop planning with language models thing people have been doing, where they do say like, here's your API. And then you can make API calls. My hope is that I can take that, you can make API calls thing and strengthen it with this basically planning rules inductions. But we do, yes, we do not induce the API by itself. That would be really cool and much harder.
So I mean, so the robot API would just be pick up a block, right? Single block. So for unstack, we just call pick up object two. Right, there is a discrepancy.
I think that's fair. Yeah, that's fair. We do have to change the API knowing that we're about to do logical planning. That's a totally fair criticism. Okay, so we sample our concrete domain file. Again, just binary choice on each of these options each time, and then we can run our symbolic planner. So we get perfect plans. And if our perfect plan is wrong, because our world model is wrong, then there won't be a path to the goal, we'll fail. We'll let the language model try to finish the plan. So here we are moving to like a little bit more recovery. If our execution fails, we'll switch over and say like, okay, language model, have at it. Like I tried with the planner and I failed. Sometimes we succeed once we're using the language model. Sometimes we get to another failure and we give up. But throughout this process, we can then hypothesize new action semantics. So here's the big horrible loop. We've got our initial trajectory, which will come from the domain file and the problem file. We try to run that in the environment. That gives us a set of valid actions, like the things that we took up to whenever we failed. State transitions, which since we're in a purely symbolic domain, we have a fully observable world. We can see exactly what changed each time. That makes post-condition induction fairly trivial. And we get an error message from the symbolic environment when we fail. Often the error message will include some either direct or indirect hint about what precondition wasn't met. So this is, in this sense, it is causal in that we have fully observable world state, but later on we won't, and then it's a little trickier. Then we use another language model to predict action semantics. This is a combination of just like straight up regex for some of it, because for things like state transition, if you're fully observable, that's easy, and then language model for others. Questions?
So, sorry, I want to understand what this feedback and this environment is. It sounds like the environment actually is literally running a PDDL executor and you're giving traces. If you're acting in the real world, you don't get such clean feedback. You actually get things like the plate broke.
Yep.
The plate broke, or you try to put something in the fridge when it wasn't clear, and you create a mess or something.
Yes. All of this is true. This loop works if you get these feedback bits. In the real world, you don't get these feedback bits, and so the next part of the next work that we follow on with is let's do this in the real world, so we can figure out how to estimate these.
Okay.
Yeah. So we're more just showing that if you were able to get this kind of like gold feedback from the world, you can induce plans.
This is rather reminiscent of counterexample guided synthesis CGUS in the.
I don't know this one.
CGUS? Okay, we should talk more
Okay.
about this. Okay.
I update my memory based on my hypothesized pre and post conditions. This is our little Bayesian update to each rule. Sample a new file, run our symbolic solver, and then if we don't get a solution, we go back to the language model to help us fix it. Or if we get a failed execution, same story. Eventually, we'll get a trajectory that succeeds. Meaning that we don't crash. Once we don't crash, we see if we actually met the goal conditions. If we do, we're done. And we say, I've learned enough about the world that I can solve this particular goal. If not, we just go back to sampling. Okay. As several questions have pointed out, this problem has been made so toy that, of course, you solve it. So in all of our planning domains, we succeed at fully recovering the pre and post conditions of every action in the environment. This is the barman domain, and what I'm showing is the ablations for the full system we call Psalm, and then just without different little bits, like without the regex, without doing the language model to guess post conditions, without doing some preemptive prospection to see if we think we're going to fail while we're planning, etc. And so for all domains, our full system works best, and for all domains, we fully recover the pre and post conditions. So that result is weird to show because it's just 100% on everything. This also works across different language model backbones. So we were using GPT-4 originally, but we also tried 3.5 and Mistral. And for each of these, what we're seeing here is the number of environment resets and then the number of individual steps that you take in the environment. And so GPT-4 does it fastest at like a minimum of 20-ish to 30-ish steps. But then the other language models are still able to do it.
I hate to keep on.
Yeah.
Talk. Do you find that like domains that are sort of highly represented probably in GPT's training set are things where like it's able to fill in a lot of details more quickly?
Yeah.
Yeah.
In fact, in the next work, we started just when the domain arrives before executing in the environment at all, make guesses about pre and post conditions. And for domains that are too well represented, that will just solve it. And then we don't test on those because we already know that that's actually just cooked in. So
Gotcha.
You can do what Route does and just garble the
true, the predicates. The problem is if you change up the semantics to language model, this trick doesn't work anymore, right? Because we're really relying on the fact that the language model is cheating, right? That's like the whole reason LLMs work is that they're cheating, right? They've seen the test data because they've seen the whole internet.
Yeah, I think you like ICAPS and all of your predicates no longer look like words. This would start to fall
Right.
apart.
Yeah, like this works for the same reason that like the old spider challenge stuff worked when people were doing language to SQL, right? Like language to SQL worked even pre-deep learning because people name their databases and their tables and their rows with intuitive things that correspond to what they're actually meant for. And this is the same kind of intuition. But yeah, if we randomize the domains with like symbolic predicates that don't have language correlates, then this falls apart, or at least works much, much more slowly because the language model is no longer helping. Okay. But like a lot of people have pointed out, we've like combined these things. We now get cheaply defined domains and perfect plans, but we've made some pretty unhinged assumptions here, like sensory observations. The world state is not actually fully observable. Like we don't know what the world is. We need to estimate this directly. We need to estimate state changes. Even telling what the effects of our actions are, telling that we failed is not straightforward. Like failure detection is its whole own problem in robotics, right? So as people have pointed out, these things make the contribution of this work like purely toy. So take the next step. We're now going to use large pre-trained models to estimate the state of the world at each time step. And that will include trying to do failure detection by seeing, does the world look like I expected it to look? And then given how the world looks, can I estimate what changed so that I can get post conditions? And now we're moving more into a sort of like trying to infer what changed in a causal manner based on our actions. We do still need to assume, to Peter's question about causality earlier, we do still need to assume we are the only actor in the environment to make this work. And I think that is a common assumption in robotics and in like control simulations. It's not one I love because it doesn't play nice with HRI. But for now, we are assuming we are the only actor. So if the world changes, it changed because of me. So we call this visual Psalm. We start by exploring the environment. So just run around, run segment anything on everything, and build a semantic map. So now I know roughly what objects are in the environment. I know where I need to stand to be near an object. And that lets me translate this semantic map into a symbolic domain file where I can say like, okay, here's like some locations. The locations correspond to places I was during my tour. I keep those on my map. Now I've got concrete locations. I know there are objects at locations because I was near them when I got there. So we do this pre-processing step basically where we walk around the room and build a domain file that represents symbolically the stuff that I can interact with. And this is the big horrible loop again. I won't go through the whole thing, but it is roughly the same loop, except for this fun part here, where now when I fail, I need to figure out why. And so what we're doing here is actually predict the error message using, again, large language model. And that's basically taking the most trivial thing you can do is take the before image and the after image and feed it to GPT-4 and be like, please tell me what changed. Obviously, we have to fine tune a lot more than that, but that's the upshot. And try to get what was unsatisfied. Why didn't we reach the goal? We do a similar thing for the causal model of like what changed in the world to get post conditions. But by doing this, we can get this list that was pointed out a second ago is not realistic to have unless your environment is like very nice to you. So we try to estimate this list. What did I do that worked? What observations did I take? And then given those observations, I can try to guess like how did I change the world at each time step? And I get my error message, but my error message is now not coming from the environment, it's coming from a language model or language vision model trying to estimate what could have gone wrong here. Like I tried to open the fridge, I tried to put food in the fridge, but the door was closed. Luckily, it's hard to break plates in AI2 Thor. You can do it, but it's hard to do it with the API controller. But this was mostly in simulation, which is boring, but it works well. So we looked at the Alfred data, which is something I put together during my postdoc for AI2 Thor. It's language guided commands for a little simulated house environment. We've got direct planning with a VLA. So like just give GPT-4 the task it's supposed to do and give it observations and do planning at each time step, like let it take an action, give it the new observation and the goal, let it take another action. That doesn't not work. Like Claude and GPT-4 can both do it, but we do it much better. And then once we've got this domain file, we can do it for new tasks too. We've got a better generalization here. We also looked at Overcooked, which is a 2-player symbol environment that's used in RL chunk and that one of my students have been playing with. GPT-4 has seen enough Overcooked that it solves it. Claude doesn't, and it's almost fine at it. That one's fun because it's multi-agent. Like you gotta take actions for 2 things at a time. That makes it a little bit more fun. BDL's not good at that, it turns out, but okay. But we did put it on a robot. And there's a totally fair criticism for what I'll show you, but I'm still going to show you. We put it on blocks world. Put the yellow block on top of orange, green on top of blue. And then this is a test time execution. So training time, RL style looks the same. It's still blocks world, it's just not this particular command. And then we show that once we've done our domain induction, figured out the rules of the world, we can do this. The totally fair criticism is blocks world is absolutely inside of these large language models. So of course it can estimate the pre and post conditions. So what we're doing now, and what I hope to be able to submit sometime this year, is something closer to robot scientist, where we've got little apartments set up and we're actively predicting like how can I learn the affordances of my own body in here? Like what can I pick up? What can I open and close? And that'll be a lot more fun. It's very specific to like this robot in this environment, so it shouldn't be as easy in the training data. Okay, I'm gonna do it on time. So I'll spend a chunk of time on our work on introspection and interaction. This work started when we, was it RTX, I think, one of the robot transformers came out, and we were running like the Franca arm, and I said like, give it a command to push its gripper into the table. And sure enough, then like hit the E-stop because it's going to break. It ought not to have done that, right? But like it's enough in the training distribution that it's like, oh yeah, I can push gripper against a thing and the table's here and it'll just do it. And so we started working on introspection and interaction to decide when models ought not do their predictions or like should hold their predictions, both in language and in robot control. There's a paradigm for this called selective prediction in the classification scenario. So in classification, if I'm giving you a question, like this is just visual question answering, what is the relationship between these 2 players? If my model thinks the word opponents is correct, but we have some way of estimating confidence and it's less than half confident, this is not a high stakes scenario, but in a high stakes scenario, 40% is absolutely not okay, right? I should say like, I'm not sure. This is the selective prediction idea, that if you're below a certain confidence threshold, you should just withhold your answer. And there are different scoring metrics for like how many questions you choose to answer versus how often you're right, that are precision recall curves you end up trading off in this paradigm. And so with selective prediction, our paper at ACL last year, we work on ways to treat VLMs as tools to do additional calling, to say like, okay, I can't answer that question, but I could answer related questions that help me build evidence for my possible answer. So we treat this as like a hypothesis reinforcement problem using basically counterfactual questions. And so then I get, yeah, I'm pretty sure they're opponents, and I spend time first doing some introspection before giving that answer. So we do this by, we have some way of estimating confidence of our language model. Here we're using a calibration set to do Platt scaling on the logits of the outputs of the answer here. If we're confident, we answer. If we're not confident, we back off to this information gathering loop. We're first going to give the image to a language model and say, generate some questions about this image. And it'll generate questions like, do the men look like they're competing? Are they standing on a court? What color are their shirts? Are they standing on opposite or same sides? We run that confidence estimator to see like, okay, like these were the questions I got. Here's the answers it gave. Do they look good? Do we feel good about the answer? And this basically helps us only look at questions that are in distribution for the VLM, which is really what we're trying to adjust here, right? Like we've got an out of distribution question. And so we're trying to ask in distribution questions that we can actually answer reliably that might help. We also look at how our hypothesis entailment would change if that were true. So this is the counterfactual bit. We say like, if their opponents and they're standing on a court, if they're standing on a court, I become more confident that their opponents, if they look like where's the good one? If they look like the colors of their shirts are white, that actually doesn't change whether I think they're opponents or not. And so here I've selected both things I can answer and things that are relevant to the topic. And then I drop the VLM entirely and just back off to really well-calibrated natural language inference models. We drop off to an NLI model and say, okay, here's the caption. Men are standing on a tennis court. Here's what I learned about them. They're standing on opposite sides of the net. Do you think these players are opponents? And we let an NLI model decide like entailed, not entailed, contradicts, right? And this gives us another confidence measure that we can use for our selective prediction. We're very sure that this is entailed, and so we can say, okay, I should answer opponents. So we evaluate on two big data sets, AOK VQA and VQA 2.0. We're looking at recall, which is the percent of predictions that I don't abstain on, so the ones I do try to answer at all, versus risk, which is basically 1 minus precision. This is how many I answered and got wrong. These are the metrics that the selective prediction folks like to use. I prefer a PR curve, but here it is. So lower is better for risk. And what we're seeing here are circles are the base model, where I just have a threshold that I've picked based on a calibration set, and I abstain if I'm below the threshold of confidence. And stars are when I apply the same model, but with this extra loop where I try to gather additional information. You can see in all cases, our recall increases. We answer a lot more questions. In all cases, the risk also increases. We've got a tolerance threshold set here, which is used to decide when I should abstain. And we can see in all cases, we do exceed the tolerance threshold on AOK VQA. We're a little bit better on VQA2, especially for the instruct blip models. So risk goes up, recall goes up, but we are controlling the risk a lot more than if we just change the threshold and insert more questions. I also found this year, we'll present this at EMNLP later on. This came from one of my class projects recently on selective prediction with VLMs, where we're looking at entity linking failure. So like really zero in on one particular kind of failure that can happen here. So if I ask a VLM in what year was Stonehenge legally protected, no problem. If I say in what year was the landmark in the image legally protected, wrong. And like, so we know it knows the answer, and we know this is Stonehenge. We've got another validation here where we say like, what is the landmark in the image, and it must answer Stonehenge, and then we include it in the test set. So we know it knows what Stonehenge is. We know it knows when Stonehenge was protected, but when we try to get it to do both at the same time, it fails. And it turns out you can kind of like see this happening. So what we're looking at here is the cosine similarity of layer 1 to layer 2, layer 2 to layer 3, layer 3 to layer 4. So you're looking at how much the logits of the individual layers in the network are changing as we do the forward pass. And if you see this, when we look at the bins of successful image pairs, like where this question was answered correctly, we converge a lot sooner to like what the network is gonna say. So it's changing much less. Like it processes the question, the logits are changing as it does some reasoning probably, and then it like knows what it's gonna say this whole time, and the logits aren't changing much till we get to the top. By contrast, if it's gonna get it wrong, it starts flailing, and we can see it flailing. It's like this is it trying to decide what the thing is. As it uses additional layers, it's running out of compute, and then it gives an answer that has low probability because the logits are all distributed by the time we get down here. Does that make sense? And you can probe for this. So we can train a probe on top of like a particularly sensitive layer. I think we use just like the one in the middle, 10 or 15. You can learn a probe on top of this on the training data, for which that just binary classifies whether you're going to get it right or wrong. And you go from just using a perplexity based, like what was the logit as a way to abstain on your coverage and risk. When you do this probing and we ensemble that with perplexity, we get huge gains in coverage. Little bit gain in risk, but often we actually decrease the risk profile too. So this is like the very effective way to tackle one particular kind of linking failure that we found in VLMs, which I think is fun. Okay, perplexity. It turns out token perplexity like doesn't actually correlate with task success. So I mentioned earlier we use plot scaling for ours. Ours is the blue curve here. This is prediction accuracy versus prediction confidence for different ways of like probing how confident are you in your answer. And so you can, with enough calibration data, you can learn some kind of like calibration curve to fit this thing closer to x equals y, and then this method works. But on a lot of data sets, this curve is like a U. Like if it's totally wrong, it's very confident. And if it's totally right, it's very confident. And we've known about this problem in ML forever, right? And so getting this like x equals y shape is actually quite tricky. You need a lot of validation data, which we don't have in robots. If I look at RT2, I'm not going to get Google's data for this. I'm certainly not going to get their validation data to run a calibration set so I can tell when I'm actually confident in the action I'm about to predict. So calibration is this big validation set, no matter what confidence estimation method you're using, all the way from this simple complexity thing up to conformal prediction. The bigger my calibration set is, the better my estimation of whether I can succeed. We just don't have this in robotics often. So evaluating generalization in robotics is hard, and we've been working on this a bit. This is a collaboration with UW that we released at RSS last year. This is some failure cases where we've got a pre-trained, RL pre-trained policy in simulation, and then we're just making simple changes to the environment that cause failure. So we turn the spatula red. It hasn't seen red spatulas before. Now it can't scoop. We change the table color to being pink, and now it can't do cup stacking. Similarly, we changed like the lighting from pure white to pink, and now I can't even do like block sliding. These very atomic tasks failing for environmental changes that are not totally unreasonable, right? If I turn the light, well, we all know if you turn the lights on and off, the robot policy gets in trouble, but it's not ideal, right? This one's fun. We changed the size of the thing, and now it can't find the handle anymore because it probably wasn't ever finding the handle. It was just memorizing where the handle was. And the fun thing, this is like a test suite. You can throw if you've got a VLA that you want to test in the gym environments, you can pull this thing down. And the fun bit is that it correlates with real results. So I'm going to show you a really terrible graph in a second, and just trust me that the things are all going the right direction. So we ran this in the real world on a couple of tasks. And then this is one big horrible graph, which is the result distribution between simulation and real. When you plot this as regressions, this is the most horrible graph. You see that except for two of them, they're all going in the right direction. They all correlate with each other, which means if my policy is failing or succeeding in sim, it's likely to fail or succeed in the real world too. So this is just a cheaper way to do this kind of evaluation, to get an initial calibration of some kind to see when your robot might be failing without having to physically run experiments to do it. But I like physical experiments. And so we've also looked at just trying to reduce experimenter time. And here we're doing taking inspiration from NLP contrast sets. So if I've got one robot that's going right past the couch and then stopping at the table, and then I change just one bit of the instruction, I change left to right. If you think about language embedding space, left and right live almost on top of each other, right? They appear in almost all the same contexts. Like they're most differentiated by political articles probably, but they're going to live like in domain space really close together, which means the VLA that's doing robot control needs to learn to separate left and right out of the language space and put them very far apart because they actually correspond to totally opposite actions. And so this is tough. And this is like a particular thing we should be looking for as a failure point.
So the thing that stands out to me there is, say that table, there are actually two tables, right? So when the robot is going left, I would have expected it to stop at the first table.
Oh, the little nightstand.
Yeah, no,
Oh, this thing.
I don't know there. Oh, that one.
Yeah. Fair enough. I think it thinks those are nightstands. This might be because of the segment anything as the backbone calls these nightstands, not table, but fair enough. But visual perturbations are also important. Like if I swapped out the table for the nightstand, I would expect different behavior. So traditionally, when we're doing evaluation, we're machine learning people, we do IID samples from our test set. Here's IID samples. I have a language instruction, I have a particular apartment set up, I have a start and end point for the robot, and then when I'm done, I rearrange the apartment and give a new language command. This is expensive physically, like I'm moving furniture around a lot. This guy knows.
Yeah.
So what we propose is like, let's actually focus in on what we know can go wrong, what is likely to go wrong. This is an idea from NLP to kind of probe the boundary of every test instance rather than just IID sampling. So I'll start with my first test instance. And then what we did is we had undergrads who don't know anything about robotics, who haven't played with it before, come in, read the instruction, And then we just tell them, just give a new instruction, like just say it differently. And so they rephrase it. Turns out when you rephrase the wording, even just to this little bit, the failure rate jumps to 100 for our VLA. Like, and this like shouldn't be out of distribution, right? This is bonkers. We can also do things like here we're changing out bookshelf for table. So we just change the stopping point from near the bookshelf to near the table. We can change a little bit of the environment. So if I rotate the couch, I should still end up at the same place, but my trajectory is now different because I don't need to go around the couch. I can change a little bit of the scene, like I can remove the bookshelf from one spot to another. And for each of these, I'm either just changing the language command, which is roughly free for robot evaluation. I just sort of pick the thing up and put it back at the start point. And then I'm moving a piece of furniture, maybe rotating it, moving it to a different place. And so I'm minimizing experimenter effort. In the paper, I really wanted them to measure that in joules, but they wouldn't. This is the upshot. We were doing IID sampling. IID sampling across your test space is expensive because you're physically having to reset things, and that costs experimenter time. Experimenter time is money. And so if we move to this contrast set evaluation, we might pick a smaller subset of the test data, but we're going to probe a whole region around each one of them. And ideally, this leads to a better calibration set for being able to decide, should I execute this policy? Am I going to get this correct or not? That'll be the next step. And the upshot is that this works. So this is standard IID evaluation. What we're looking at is the error in our running estimate of how far away from the goal we get on average across the whole test set. So we converge to zero, right? Like when we've seen all the test instances, we have exactly the average error that we got over all of them. And then on the the x-axis here, this is cumulative cost. They didn't use joules, they used distance. So we're just measuring how far the center of mass of each object moved across the different instances. And so we see that by about, what is this, like 1/5 of the evaluations, we've gotten within like 5% of the true error on just like much less experimenter time and effort. And so we propose this as a way to, again, like this in-sim Coliseum evaluation, a way to quickly tell if your VLA is just going to fail, because we can get quite close to the final error with much less time by just doing this contrast evaluation and quickly looking at possible failure points.
I just noticed it's a Barr's paper too.
Yes, yeah, this is all Barr's work. Yeah, Barr's was from the FRI program here, working with Justin and Peter, is now my PhD student who did this.
I can also see him refusing to do it, Joel CQE.
Yes.
He can be very stubborn.
Yeah, he didn't want the couch to be like unique in the optimization process. Okay. Also, Barr's work, we build on this core idea of trying to estimate like when we're going to fail by looking at existing evaluations across different policies and tasks. And what we want to do is, let's say our problem formulation is I've got 5 VLAs. I want to determine which VLA I should use on my robot. Maybe I want to switch which VLA I'm using depending on the task, because different tasks might succeed with pi 0, like folding laundry, but they're going to, like folding laundry fails on everything but pi 0, right? And so what we do is we build a little surrogate model where we embed a task description using a language model, embed a policy either with a random vector, or you can do like task style embedding where you look at the training data of the thing and build like an average vector. That turns out to work really well because policies that have the same training tend to operate similarly. Then you learn a projection, very simple. The projection predicts mean, variance, and overall performance. So whether we think we're going to succeed or not. And then we can use Bayesian active learning. So add test time dropout to this prediction to get variance on our variance prediction, variance on our mean prediction, and then get these possible outputs. So when these possible outputs look very different, so here I've got like, if I tried lift eggplant with OpenVLA, I predict I'm going to succeed with this likelihood, and then I apply this test time dropout to get different possible curves of success. These look very different. And so I can calculate the expected info gain if I were to add another sample, and I estimate like if I added a sample and it was correct, if I added a sample and it said that the trajectory failed, how much would this variance go down in my sampling? That gives me a rough estimate of which experiment is going to tell me the most about this grid of different policies and tasks. And I can weight that against the cost, which is if I change tasks, I've got to physically rearrange the table, right? So I've got a cost associated with changing tasks. If I just run a new policy, again, like language, that's kind of free, right? That's just changing the code in your command line. versus having to actually change the table up. So this is the basic idea, and this lets us train up this task and policy matrix. This is really closely related to recommender systems for matrix completion. Like if you've got a set of people and a set of movies, and you want to see like this person liked this movie, and this person is similar to this person, so they might like this movie too. This is the same idea. And so we actually work with one of our machine learning faculty on doing this right, because I wouldn't know. But this algorithm, the way that we formulated it, converges to a set such that the max on each row, which is the max on each column corresponds to the policy that is optimal for that task. And that's what we get as output, is a matrix where we know for every task which policy is most likely to succeed. And we can do that by considering experimenter cost. We can make that guarantee stronger the more samples we get. But at every sample, we can say with confidence, like with this amount of work that you've put into it, you have the best estimate of which policy is going to succeed on this task.
So this is like information gains contrasted with effort. It's like,
Mhm.
it's almost like a decision tree with like both those things back. Or like an old school decision tree with both those things back.
I think that's a fair way to characterize it. Yeah, you're building a dumb J48 tree by deciding which experiment to do next.
Yeah.
Okay. Let me check the time. Ray, do you want me to stop at 11:50 or do I have 4 minutes?
You can have 4 minutes now.
Okay, I will briefly talk about processing beyond text, which is the thing that I'm actually most excited about. I'm going to skip speech. Actually, I'm going to show you this one because it's funny. If I am in an environment with a robot and I give a speech command, this came up all the way back in grad school. I had the idea for this paper and it took a long time to find some undergrads who wanted to do it. I give a command. My text to speech says, or sorry, my ASR says, wash the dirty pug in the sink. So all we do is add the vision. You take an off-the-shelf speech recognizer like Wave2Vec, throw in a clip embedding that already has some language information coded into it. Clip is roughly like bag of visual objects. So we throw a clip embedding in, train like a small LoRa style backprop through the Wave2Vec, and then make a new prediction of what the ASR was. It turns out it takes like very little data to make this work well. So we go from original audio signal, we created training and testing data by noising it out, like just add white noise or add like the sound of a blender or something. And then show that once we've done this training where we have visual information at the same time, it's that when I tell the robot, wash the dirty mug in the sink, it's also looking at the sink with the mug in it, and the clip embeddings basically give the speech recognizer a strong prior that I'm talking about either the stuff I'm looking at or at least stuff in the kitchen. So we don't get like the dog, it doesn't show up anymore in the vocabulary. So I won't go into the details of that, but I think that's fun. And it works really well, including extrinsically, like increases the task success on these noisy things. I want to start working on sign language more. I'm taking ASL this semester. One of my students just graduated who was a fluent, worked as a translator before coming to grad school. They're now at Gallaudet doing a postdoc. I want to do gesture recognition on robots. Sign language is harder. If I can do signing, I can get to do both at the same time. The upshot is that like tracking has gotten a lot better from the computer vision side in the last couple of years, and you can almost do fingers now. And if you can almost do fingers, you can almost do signing. And so the state of the art up until we beat it 2 years ago was this graph convolutional network that takes the skeleton pose and then predicts like a single sign. So these are isolated sign videos. It's a person doing a single sign in the video, which also super unrealistic. It's like a word classifier for speech where you're only doing one word at a time. That's where we started. So, and we found basically that if we incorporate phonological knowledge, we improve predictions a lot. Phonological predictions come from an intuition from speech. So we've seen in speech recognizers, this is the A.V. Hubert model, where you read somebody's lips while you're doing speech processing and then it improves. Not everybody knows this, but like, you remember during the pandemic, you suddenly couldn't understand anybody? This doesn't happen because the mask muffles you. It happens because you can't read lips anymore. This is a huge part of audio processing. And so with signing, we can actually see all the phonology. With speech, you can only really see like plosives on the lip. You can't see anything, like you can't see your glottis, right? But with phonology, with signing, you can see the whole body. Like every part of the sign's phonology is visible. And so there's like a lot more power to this kind of auxiliary loss. And so we basically just threw in an aux loss that says, hey, I know hand shape is important. Like if the person is doing the Y hand shape, it like limits the number of possible words they could be saying. If they're doing B, it limits the words they could be saying. And we look at the location. These are two major pieces of phonology in signing, like where the sign happens on the body, where it moves, and what hand shape it's being made with. And it turns out if we just throw these in as auxiliary predictions, this is sufficient to cut down a bunch of the spurious correlations this classifier learns, and we get like much higher performance. I hope I have the results here. Yeah. So this is on all the test data. Accuracy jumps up a bunch when we include phonological information. What I like a lot is this is the test set for whom at training time there was phonology information. So the ox loss existed. We've also got signs in the test set that at training time we didn't have phonological labels. So we're only applying this ox loss when it's available. Sign data is really sparse. It turns out we get a big boost even on the signs that we didn't have any information for. So like we are successfully reducing spurious correlations. It's not just learning it for the signs that had labels, which is really fun. And this works regardless of the backbone. Like we used the state-of-the-art SLGCN to do it, but then we ran it with just a vanilla transformer too to show it that the backbone is not unique here. It's the ox loss. So with a transformer, the performance is all lower, but our gains are about the same. They're the same error reduction. And I won't talk about the next thing because I'm out of time, but the upshot is that it's very cool. We're gonna figure out what phonology is without labels. We actually already did it. It's in submission. It's really cool. There's no labels for face on any of the things. Like you can't tell these apart with phonology because the labels in existing taxonomies don't label face expressions, facial action units. But in our thing, we like use vector quantization and code books, and our face code book has like they corresponds with the actual meaningful. That's really cool. I hope the viewers like it because the student's gone. Okay, I talked about language logic, introspection, interaction, and processing beyond text. Not as much as I wanted to. Thanks to all my students, including Lee, who did the sign language work, who's now at Gallaudet, and Jesse, whose work I didn't talk too much about, but now just joined UW as a postdoc. I'll graduate almost the rest of these people all this year, and so I am hiring if you're interested or know someone who is. Thank you.
One thing I just noticed, someone dropped off the schedule and there is an opening at 2, if anyone would like to talk to Jesse now. But yeah, open for questions. Get some during the talk. I'll just start with I'm getting confused. What are you calling phonology and sign language? I'm not sure. I didn't get that.
Phonology in the IPA sense. So we've got like the International Phonetic Alphabet is roughly all the sounds we make in Western languages, right? The phonology for sign language is stuff like what is a minimal pair of differences. So like if I make an identical sign but with a different hand shape, it's on the same part of my body, same facial expression. If that has a different meaning, then we would call that phonologically meaningful. Does that make sense? Like if I make the same sign but with Y versus B, and this means 2 different things, then this must be like.
Yeah, I mean that's a specific because usually phonology is about sounds, right? Which you obviously don't.
So there's a term called like chireme that is sometimes used for this, but my understanding as a person who is not in the deaf and hard of hearing community but talks to them a bunch because I don't want to look like a total ass, chireme is like not a generally accepted thing. They prefer phonology, even though that's like about audition.
So in this, like, the sign language architecture you showed with the auxiliary losses, it reminds me a lot of kind of the sort of post-neural, like, things that were happening with like syntactic features where people were like, this is no longer a good like input feature. I don't want to put like my syntactic parse in the input.
Yep.
But you know, actually, there's still some benefit to be had by having an auxiliary loss that like predicts syntax and that helps me kind of learn things. And those things have largely gone away because of scale. I assume with sign language, the scaling problem is that there's just not that much data.
The bet I think I can reasonably make, and that my student made with their thesis, is that there will never be enough data for signing. Like the population is just truly much smaller. There are like hearing signers outnumber deaf signers by like an order of magnitude.
Yeah.
So there's very little data and even less that's clean.
Yeah. Is there any sort of opportunity for synthetic data where like if you have like a, you know,
if you've got a good
3D
skill
model,
pose, I think so. I think that's an interesting direction. I'm hiring in this direction. If I get a student who wants to do that, I feel like, skeletal pose modeling is pretty good. Diffusion for pose prediction is pretty good. If we can get it for hands, I think that's totally reasonable. And then we could get something that looks more like weird automated sentences, because right now almost all the work is also in isolated signs. Doing signing sentences almost impossible. Like signs blend together, they happen across the body and more like speech, right? It's like doing sign translation is like if you were going to transcribe English speech in Russian without going to English first, right? Because ASL is its whole own language and it doesn't have a written form. So to go straight to English is basically bypassing a whole latent language, which is also really hard. So yeah, synthetic data would be cool. Probably that's the only way to get forward with scale.
I'm not the expert in this, as far as I know, like signing left-handed or right-handed, how do you deal with this?
How do I what?
Like, how do you deal with those like left-handed person or right-handed ASL speaker?
Yeah, this is a good question. So one-handed signs, and I might be wrong. I'm taking ASL 1. I'm 2 weeks in. I'm a left-handed sign, and it turns out. One-handed signs can be made with either hand. The speaker usually stays with that hand. So if you know which hand they're going to be using, it should be okay. In our data set, I believe all of the signers either were right-handed or when they're left-handed, we flip the video because it's labeled. And so it looks like the hand is always where we expected it to be, which is important for the graph convolutional network backbone. Yeah, it expects one hand to be doing the bulk of the meaning.
Any final questions? Okay, well, let's spend just a little less time. When's our next speaker, actually?
The 19th.
The 19th, so I guess we have a little bit of a gap. I tried to get, we always try to get people to come early in the semester, it's always hard. But so we have a bit of a gap, but we hope to see you on the 19th. Who is that actually?
Next time.
Next time, I'm supposed to.
Yeah,